Hello, this video is a short summary of thesis work on improved oil recovery using advanced control. This thesis was done as a part of master's course at University of Southeast Norway, Porsgrunn. I would like to thank my supervisor, Professor Bartley, and external partner, Juan Videla from Equinor. Oil reservoir is a porous rock which has hydrocarbons trapped in it. In order to maximize the oil production, it is necessary to predict the future behavior of the oil production. Oil reservoir simulation is one of the techniques to predict the future behavior of the oil production. And advanced control strategies is one of the enhanced oil recovery technique to maximize the oil production. Now, the main objective of this work is to implement a 2D control relevant oil reservoir model using Julia programming language and to predict the uncertainties in the oil reservoir simulation. And finally, to maximize the oil production by incorporating advanced control strategies such as PI controller, model predictive controller. Now the model overview. The oil reservoir model is mainly based upon the mass conservation equation. These models are comparatively complex, so to simplify the model, some of the assumptions are made. First, the reservoir is considered to be two-dimensional. Second, only two phases, that is oil and water, are assumed to be present. Third, capillary pressure is assumed to be zero. Fourth, the homogeneous dispersion of water is assumed. Fifth, homogeneous reservoir in terms of its permeability, porosity are assumed. Sixth, constant density, viscosity, and formation volume factor is assumed. For the well model, the well flow equation is derived based upon the assumptions that the flow is radial and steady in neighborhood of the well. This equation is also called Peaceman equation. In order to simulate the model, the 2D reservoir is divided into 400 grids. The number of grids along the reservoir length is set to be 20. Also, the number of grids along the reservoir radius is set to be 20 as well. The total simulation time is set to be 1000 days. The inflow control valves are placed at every 60 meters of the well length. The 5-instance stencil scheme used in our model discretization is shown in the bottom of this slide. The model was solved in a Julia using standard differential equation solver package called differential equation or JL. This figure demonstrates the production of oil and water. The maroon line indicates the flow rate of oil, while the blue line indicates the flow rate of water. At around after 390 days of production, we can see that the production of oil is decreasing. This point of time is called water breakthrough time. The model uncertainty in the oil reservoir is predicted by a Monte Carlo simulation. The Monte Carlo simulation was performed in Julia using parallel ensemble simulation. The parameters like rock permeability, porosity, initial water saturation in the reservoir are varied by plus minus 20%. In this figure, we can see that the uncertainties in the production of oil and water. The implementation of PI controller. A PI controller was used in this work to control the ICV's opening in order to minimize the water cut. The ICVs are grouped into 4 groups, each containing 5 ICVs. These individual groups will receive the control signal from the controller. In the left side of the slide, we can see that the increase in total oil production volume after implementing a PI controller and is denoted by the green line. The total oil production in 1000 days was increased by 1.7873%. Another figure demonstrates the decrease in total water production after implementing PI controller and is denoted by the red line. The water production in 1000 days was decreased by 2.5942%. The increase in oil production with PI controller is not so significant due to limited capability of PI controller, so it is recommended to implement more advanced controllers such as model predictive controller in the future. Thank you.